Close your eyes and picture this. You're standing at your front door, and your friend texts, "Meet me at the pizza shop 2 blocks north and 1 block east." Easy, right? But what if you didn't have a map? You'd be guessing every turn, maybe walking into a tree. That's exactly how a language model plans its moves, until it builds a tiny, perfect simulator first. Here's the problem. Language models are amazing at guessing words, but terrible at planning. They'll tell you to turn left into a lake because they don't know what a lake looks like in real life. So AI Labs asked, how can we teach AI to see the future before it acts? The answer? World models. Think of them like a video game level-up screen where the AI tests every move before taking it. Let's say you're a robot in a 5x5 grid room. Your goal? Grab the red apple at 3, 4. A language model tries 20 wild paths. Walk through the apple, teleport to the chair, use mind control. It's creative, but useless. A world model? It builds a tiny grid where each cell is a thing. Table sad face 1, 2. Apple sad face 3, 4. Chair sad face 4, 1. Then it tests moves. No guessing, just rules. Here's the math. A language model might need 175 billion numbers to learn what a table looks like. A world model? Just 1,000 numbers. That's 175,000 times smaller. And yet, in planning tasks, it can outperform the giant. Size doesn't win, clarity does. Let's meet our robot. Goal: grab the apple at 3, 4. World model defines the room as a 5x5 grid. Each cell is a thing. Empty sad face 0, 0. Table sad face 1, 2. Apple sad face 3, 4. Chair sad face 4, 1. Now the robot tests moves. Move forward. Grid updates to 2, 2. Grab apple. Score +10. Walk into a wall. Score -5. It learns the best path in 5 tries. Now let's see the magic. Robot tries 5 moves. Forward, left, forward, grab. Each move updates the grid and scores it. After 5 tries, it finds the best path. Forward, left, grab. Success ratio. 5 divided by 5 is equal to 1.00. Meanwhile, the language model tries 20 wild paths. Only 2 work. Success ratio. 2 divided by 20 is equal to 0.10. The world model wins by a landslide. Why does this work? Because the world model isn't guessing words. It's running a tiny physics engine. It knows that if you move forward, the apple moves with the table. It knows chairs don't float. And it knows apples aren't teleporters. That's the power of a grounded simulation. Here's a real example. Imagine an AI robot in a kitchen. Goal: grab a mug from the counter at 2, 3. World model defines the kitchen as a 5x5 grid. Robot tries moves. Forward, left, grab. Each move updates the grid and scores it. Success in 3 tries. No hallucinations. No guessing. Just a clean, tiny simulation. Compare this to a language model trying the same task. It spits out 25 wild paths. Fly to the ceiling, teleport to the fridge, use mind control on the mug. The world model? It grabs the mug in 3 tries. That's the difference between chaos and clarity. And here's the kicker. The world model's code is just 12 lines. The language model's code? Millions of lines. So while the big model spits out words, the tiny model plans with confidence. That's the power of grounded simulation. But wait, if world models are so great, why aren't all AIs using them? Because they have a weakness. World models work best when the world follows clear rules. What if the rules break? Like in a crowded mall where people suddenly walk backward? Or if the apple turns into a banana midair? Chaos. That's why labs are working on hybrid models. Language models for creativity, world models for planning. Here's how a hybrid model works. Language model generates creative ideas. World model tests if they're safe. For example, use a ladder to reach the apple. Language model says yes. World model tests. Ladder sad face 2, 2. Apple sad face 3, 4. Move up ladder. Grid updates to 2, 3. Grab apple. Score +10. Success. Hybrid models combine the best of both worlds. Let's code a world model together. Here's a 7-line Python example. We define the room as a 5 by 5 grid. Robot starts at 0, 0. Goal is the apple at 3, 4. Robot tests moves, forward, left, grab. Each move updates the grid and scores it. The robot learns the best path in 5 tries. See how simple this is. The robot doesn't need to know millions of words. It just needs to know the rules of its tiny grid. That's the power of grounded simulation. Small, smart, and predictable. Now, let's talk numbers again. A language model might be 175 billion parameters. A world model? Maybe 1,000. That's 175,000 times smaller. And yet, in planning tasks, it can outperform the giant. Size doesn't always win, clarity does. But what about humans? We don't have trillion-parameter brains, yet we walk across rooms without thinking. That's because we run tiny inner simulations too. Our brains guess where the floor is, where the wall is, and where our foot will land. We're using a world model, just one built into our heads. So, world models are like cheat codes for AI. They let it plan safely, avoid hallucinations, and act with confidence. And the best part? They don't need to be huge. A tiny, grounded world model can outperform a giant language model in planning tasks. That's the revolution. Let's recap. A world model is an agent's inner simulator. It's a tiny, rule-based copy of the world where the agent tests moves before acting. It avoids hallucinations by following clear rules, not guessing words. And it can outperform giant models in planning tasks, because clarity beats size. So next time you see a robot planning a route, remember, it's not just a giant brain spitting out words. It's probably running a tiny, perfect inner simulation first. That's the secret to its planning power. But world models aren't perfect. They struggle in chaotic worlds, like a crowded mall where people suddenly walk backward, or if the environment changes too fast. That's why labs are working on hybrid models, language models for creativity, world models for planning. It's all about the right tool for the job. So while world models are amazing for predictable tasks, they're not the end-all. They're one tool in the AI toolbox. And that's okay, because AI isn't just one thing. It's a mix of tools, each with its own superpower. Now let's talk about the elephant in the room. Why are big labs fighting over world models? Because they unlock the next level of AI. Robots that fetch packages, cars that avoid pedestrians, drones that map forests. World models make AI safe, predictable, and useful in the real world. But here's the catch. Building a world model isn't easy. You need to define the rules, the grid, the physics. It's like coding a video game, but one where the player is real. And that's why labs are racing to crack it. Let's try another real example. Imagine an AI drone mapping a forest. Goal: reach the tallest tree at 10, 20. World model defines the forest as a 25 by 25 grid. Drone tests moves. North, east, scan. Each move updates the grid and scores it. Success in 12 tries. No crashes. No guessing. Just a clean, tiny simulation. Compare this to a language model trying the same task. It spits out 40 wild paths. Fly into a bird, teleport to the tree, use mind control on the drone. The world model? It reaches the tree in 12 tries. That's the difference between chaos and clarity. And here's the final kicker. The world model's code is just 15 lines. The language model's code? Millions of lines. So while the big model spits out words, the tiny model plans with confidence. That's the power of grounded simulation. Ready to build your own world model? Next time, we'll code one together, from scratch. You'll see how a 7-line simulator can outplan a giant language model. It's simple, it's fun, and it's the future of AI planning. If you love this breakdown, hit subscribe. We're diving deeper into AI's inner workings. No jargon, just clear steps and real code. See you next time.